Apologies for the weird departure in part one, but sometimes it be like that. Welcome back for part two of NMR. If first part was merely concerned about theory, which is, something that has to be taught as part of ECE chemistry, this is how do you read an NMR? Because as you're about to discover, some of this is pretty tricky, but I'm going to do my best to get you through it. Alright, so this is where we left off, and it's the difference in energy needed to change the spin state of the sample compared to TMS is called chemical shift. The units of chemical shift are in parts per million. Sorry, don't know why I stumbled on that. Now, here, if we look at this, we see that this is a carbon-13 NMR. Now, we have two carbons. Both of the carbons are different because there's a CH3 and a CH2, and they give us two different peaks. So we have CH3 and a CH2. How do we know which one's which? Well, we'll get to that. Now, actual magnetic field experienced by the nucleus is not the same as the applied external magnetic field. Nearby electrons have spin, and an associated magnetic field shields the nucleus from the external magnetic field. The amount of nuclear shielding affects the amount of energy needed for the nucleus to change its spin. So, what this means is, the closer something is to oxygens, nitrogens, or double bonds, the further left you will find it on an NMR spectrum. So here, oxygen is super shielded because it's got two lone pairs of electrons. There's a double bond here, so this is super shielded. You're basically never going to see this come up. However, the CH2 is right next door to the oxygen, so it's basically like walking into your neighbor's bomb shelter. Whereas, like, the CH3 kind of tries to knock on the bomb shelter, but it's like, nah, sorry, we're full, come back later. So, for a proton NMR spectroscopy, this is where the bulk of the exam marks will be. Now, proton NMR spectroscopy identifies the number of different hydrogen environments in a molecule. Take a look at this example of propanone. Now, we both have a CH3, which is connected, both of these environments are CH3, which is connected to a carbonyl group. It is identical. If you're like, can it see anything else? Nah, not really. So, this is this one peak, and it's shown by the absorption. Wow, they really couldn't spell absorption in the textbook. But, this is the peak of energy put out by each one of those hydrogens. And it's slightly past 2. It doesn't super matter what the number is here. Now, protons in the same chemical environment are equivalent. Now, each one of those hydrogens are equal to every other hydrogen on the carbon. Likewise, all of those two are equivalent to those two on the same hydrogen. And here, these three are equivalent. As you might be able to tell, we have three different, we have three carbon environments, but because this CH2 is different to those two CH3s, that one is separate, but this CH3 sees an oxygen and then a CH2. It is identical. Now, peak area, 1 to 3. This is a thing which was always poorly explained to me when I was your age. So, this is integration. Integration is a fancy term for area under the peak. I currently teach at a school that doesn't have maths methods, so you'll excuse me for simplifying it a little. But each peak in an NMR is going to have a certain amount of area underneath it. The difference between the peaks, when I say the peak area is 1 here and the peak area is 3 here, is this has 1 hydrogen's worth of peaks, and this has 3 hydrogens worth of peaks. Now, these two carbons are identical. They both have 3 hydrogens on them. However, this carbon has 2 hydrogens on it. So really the ratio is this is a 2 hydrogen worth peak, and this is a 6 hydrogen worth peak. The difference between the two, well, that gives you an idea of how many hydrogens are relatively at each peak. All right, as the next one says. All right, let's have a look at this one, because this is showing us something a little different. Why are there 4 peaks here? Why are there 3 peaks here? Well, this is a thing that is quite significantly more unshielded. Slightly more shielded, sorry, because it is next to chlorine, which has 3 lone pairs. So it's slightly moved to the left, and it's got 2 hydrogens. Here we have 3 hydrogens, and it's about 1.5. But what is that pattern? Let's find out. High resolution NMR sees some signals split into patterns. This is due to the effect of neighboring protons. The number of lines in a signal is given by the relationship n+1, where n is the neighboring protons. Now, here, if we go, this is our peak at 3.5. Well, how many peaks are there? There's 1, 2, 3 protons, sorry, not peaks. So it gets split into 3 plus 1 peaks, where it's actually, it's 4 peaks. Whereas here, the blue hydrogens, the CH3 group, see 2 hydrogens, and it gets split into a triplet. Now, this is, my apologies, let me pause and start again. Because these 3 hydrogens on this carbon see 2 hydrogens on this carbon, they get split 2 plus 1, where n is the numbering protons. I'm going to bring something up for a second, because it's something that really blows my mind here. Have you seen Pascal's triangle? Alright, so this is Pascal's triangle. Alright, let's have a look at this one. Pascal's triangle has a really cool bunch of neat things, but what I want to draw your attention to is this 1, 2, 1, where there's 3 things on there. Have a look at this pattern. That's 1, 2, 1. If you actually look at this 1, 3, 3, 1, 1, 3, 3, 1, it actually gets split basically the same way that Pascal's triangle would. If you haven't heard of Pascal's triangle, I advise you to look it up in your own time. This is a chemistry video. What are you doing? Alright, now, here are a few splitting patterns. A singlet means a hydrogen atom has no neighbors, aka 1 peak, not split, 0 hydrogens next to it. A doublet means a hydrogen atom has 1 neighbor, aka it's next to a CH group. A triplet means a hydrogen atom has 2 neighbors, CH2, and a quartet means a hydrogen atom has 3 neighbors, CH3. Now, signal splitting acts over small distances only. The interacting hydrogens must be bonded to adjacent atoms. For example, CH3, OCH2, OCH3 shows no peak splitting because the hydrogens are not joined to adjacent atoms. They are separated by an oxygen atom. Now, here's what I'm going to tell you. Do you know, it's not in a textbook, and you're gonna not find it in a textbook anywhere, because this is a thing that's not actually explained until like 3rd year uni. So I'm going to explain it to you now. It's called 3J coupling. Now, if you try and say 3J coupling in an exam, nobody's going to give you any marks because you're not supposed to know it. But if you are trying to see whether a hydrogen atom can see a different molecule, what you need to do is you need to count the steps or the bonds. Now, I'm going to go back a few slides. Actually, yeah, let's do this one. So let's see, oh, we've got the hydrogen here. It goes one bond to the carbon, another bond to the next carbon, and one more bond to this hydrogen. It takes 3 steps or bonds to see the hydrogen. Because it takes only 3 steps, you know that those 2 hydrogens can see each other. They're neighbors. Let's go back a few more slides. Let's count out the hydrogens in dimethoxymethane. Well, this hydrogen here, 1 step, 2 step, 3 step, 4 step. Now, it took 4 steps to actually see that hydrogen, so we know that they're not actually neighbors. They don't really care about each other. Where also, this hydrogen can't see the other end of the molecule because it takes 1, 2, 3, 4, 5, 6 steps. That's so far away. I am also recording this with a broken leg, so 6 steps is a lot for me too. I'm not just blaming hydrogens because, you know, it's easy. All right. Let's put our skills into practice. This is ethyl ethanoate. Now, there are 3 peaks here. This is a quartet with 2 hydrogens attached. This is a singlet that's worth 3 hydrogens. And this is a triplet, which is worth 3 hydrogens as well. Now, what I want you to do is I want you to label, draw this ethyl ethanoate, write it down, copy paste it into Paint, pause the video and label each one of these hydrogen environments or proton environments as A, B, or C based off what you think they are already. I'm going to stop talking for 15 seconds to let you pause the video. All right, welcome back. Now, let's look at the easiest piece of information that we have. We have a singlet. A singlet means that there are no hydrogens within 3 steps. So which hydrogen environment would that be? Well, B would become this CH3 group here in the ethyl ethanoate because there are no hydrogens for 1, 2, 3, 4, 5, 6 bonds. Hence why it's a singlet. Now, there are 2 ways that you can look at splitting A and C, because clearly we still have a CH2 group and a CH3 group to go. Now, one way that you might have chosen to solve this is to look at the 2H and the 3H. That would tell you that this peak is worth 2 hydrogens, aka it's the CH2 group, or the CH3 group being worth 3 hydrogens would make it C. So if you have written down somewhere B, A, C, well done, full marks. The other way that you could choose to solve this, you could go, this is a quartet. A quartet means it is next door to 3 hydrogens, okay? It's next door to CH3, which means this CH2, it would be the CH2 group that's right next to it. Here we have a triplet, which means it's next door to a CH2 group. So this 3H sees this CH2 and splits into 3, therefore BAC, still right. Now, to interpret a proton spectra, again, look at the number of signals, it tells you the number of proton environments. The relative peak area helps you determine how many protons are in each area. And the splitting of signals. This provides information about the hydrogen atoms in adjacent environments. I've just gone through all 3 of them, so I feel pretty good. Now, the chemical shift of the signals is also a very helpful piece of information. So here, what we have is CH3 is right next to the ester group. which has both a carbonyl group and an oxygen group. This pushes the CH3 like at full 3 points of ppm to the left, versus the CH3 group, which is really far away from that oxygen. CH2 group right next to an oxygen pushes it to about 2. Like I said earlier, the closer it is to carbonyls, double bonds, or nitrogens, or even oxygens, the further left it goes. This should probably give you that information too. This is the information from the data book. As you can see, alkanes 0.9, CH2s 1.3, 1.4, alkenes 1.6 to 1.9, and then you've got your esters and your amides at 2, benzene rings at about 6.0, amides, aldehydes, and carboxylic acids, the further left you go. Here's a sample question. Now, the proton NMR spectrum of a compound with a molecular formula of C2H4Cl2 is shown below. Relative peak areas are shown on the spectrum. Identify this compound using the information provided in the spectrum. What I'm going to do is I'm going to give you 10 seconds to pause the video. And then after those 10 seconds, you can unpause it. I'll give you a hint and then I'll let you pause it again. All right, here's your hint. So the molecular formula of the molecule is C2H4Cl2. What you can do is you can actually work out already what the only 2 possible molecules are for C2H4Cl2, and then you can try and work out what splitting and integration would look like for those 2 peaks. Again, I'm going to stop talking to let you pause it. Okay, so what information does the formula provide about the compound? Well, the 2 molecules from the formula are either 1,2-dichloroethane or 1,1-dichloroethane. So here what they've done is they've put it into a table. So they've taken this and put it into a table. So here at 2.1, you've got something that's worth 3 hydrogens, and it has doublet. And then 5.9, you've got a quartet, which is a 4-line pattern. So there are 2 signals that mean there must be 2 different hydrogen environments. So you could use the table, or you could go back and just look at your diagram. So let's look at the relative peak area. Now, what this means is our quartet is worth 1 hydrogen, but our doublet is worth 3 hydrogens. Therefore, our hydrogens must be on our molecule in a ratio of 1 to 3. Therefore, we could probably say that it is 1,1-dichloroethane, as it's what fits the pattern. However, they've also used peak splitting, which seems a little redundant. There's about 4 different ways you could have answered this question. Alright, here's another one. The proton NMR spectrum of a compound with molecular formula C2H3Cl3 is shown below. Relative peak areas are shown on the spectrum. Identify this compound using the information provided in the NMR spectrum. Alright, I'm going to pause it again to let you try and figure it out. Come back in 15 seconds if you want a hint. Alright, so C2H3Cl3. What that means is, let's just take the first carbon. You can either have 0 chlorines on it, 1 chlorine on it, or 2. Sorry, that's actually right. There's only 2 different possible molecules that you can have here. Again, you can either have 0 chlorines on the first carbon, or you can have 1 chlorine on the first carbon. Otherwise, that would create, you can't go 2 or 3 because that would create a symmetrical molecule. Now, draw those 2 out and then try and work it out again. One's going to have, all right, I'm going to stop talking because I nearly gave it away again. All right, let's have a look. So, there are 2 different environments, and one's got a 1 hydrogen and the other one's got a 2 hydrogen. So what information does this formula provide about the compounds? Sorry. I could have just used my pen. All right, so it's either C. I'm going to draw it. This gives you a second to catch up. God, why didn't I start using this pen earlier? I've recorded 45 minutes worth of videos. I don't really want to go back. I look forward to the time when I can actually just sit down and do all of these videos proper. Alright, so that's our first molecule, which is 111 trichloroethane, or okay, sorry, let's just pretend I made that a Cl. It's the worst Cl you've ever seen, but it's fine. Cl, and H. Alright, now, we have 2 different peaks. One has a integration value of 1 hydrogen, and the other one has an integration value of 2 hydrogen. You can solve, like we've been doing so far, you can solve this one of 2 ways, right? I'll walk you through the first one. I'll walk you through both. Fine, let's do it. Alright, so integration. You've got a hydrogen that's worth an integration peak worth of 1 hydrogen and an integration peak of 2 hydrogen. Well, this one has 2 hydrogens, and this one has 1 hydrogen. Oh look, it might be this one, which has 3 and 0. So it's not that one. You can also tell because there's only 1 hydrogen environment. If it was truly that peak, you would literally just have that and then nothing. Whereas this one's got 2 hydrogens and 1 hydrogen. So you can solve it that way. Or you can just count the peaks, which is the second way. Third way is the hydrogen is split into a triplet, which the 1 hydrogen is split into a triplet, aka this hydrogen sees 2 protons, splits into a triplet. These 2 see 1 hydrogen, split into a doublet. However you do it, up to you. Alright, interpreting carbon-13 spectra. Okay, they have no spin and are not detected by NMR spectroscopy if they're carbon-12. However, carbon-13, well, it's kind of odd. Alright, the abundance of carbon-13 is only 1.1%, but it's very useful in NMR because they identify different carbon atom environments within a molecule. So, the first carbon, closer to the oxygen, further to the left. Second carbon, further away from the oxygen, closer to the right. Now, again, same thing. The closer it is to the shielding, the further left you'll find it in a spectra. Oh look, we have this helpful table. You never have to think about splitting or integration ever when doing a carbon NMR. Literally, it's just find the peak. Low abundance of carbon-13 means that there's no splitting, or if there is, it's super rarely, so we never display it. In addition, peak areas are not directly proportional. It's literally just, oh, this peak is at 200 ppm, so it's probably an aldehyde, versus this peak is at 31 ppm, so it's probably a CH3. Alright, so have a look at the two spectra for chloroethane. Hey, look, triplet, 3 hydrogens, quartet, 2 hydrogens, versus one peak and one peak. Easy. And I'm going to stop here because mass spectrometry has been deleted from the 2020 course. So thank you for watching. I'm sorry I went on for like 45 minutes, but this is it. That's all of NMR. You did all of NMR in a day. Go do some Heinemann questions. Bye.